Good afternoon, everyone. We'll now start. Welcome to our webinar on simulating biotechnology with Flow3D. Today we'll talk about a number of applications in the biotechnology industry where Flow3D has been used successfully. Again, I would like to remind you that you can send us your questions on the about our product through the Q&A box on the right-hand side of your screen. Also note that in order for attendees to hear this presentation effectively, the audience has been muted. Well, I'll go ahead now. My name is Shayan Palit, and I'm an engineer at Flow Science. We develop and support the CFD code Flow3D. Presenting with me today is my colleague, Joel Jacob. I'll first talk about three important modeling techniques in Flow3D. These are techniques in Flow3D which make it a unique computational fluid dynamics code. They enable Flow3D to efficiently and accurately simulate transient solutions. The first technique that I'll talk about is called favor. Favor stands for fractional area volume obstacle representation, and it's the algorithm that embeds a geometry into a structured grid. The advantages of this technique are grid independence and the fact that a rectangular mesh can simply be overlaid onto the geometry. Flow3D's preprocessor automatically embeds this geometry into the mesh by creating area and volume fractions that block portions of cells. This methodology also means that there are no momentum losses typically found in a structured grid. The second technique I'm going to talk about is the true-off technique, and you can see the image on your lower left-hand side. True-off is our means of tracking a distinct liquid-gas interface. Flow Science is the original developer of the volume of fluid method, and we distinguish our WOF, or volume of fluid method, from other such methods by calling it the true-off method. A free surface is a distinct and trackable interface between liquid and gas. Fluid fractions and other geometrical parameters describe how a fluid is positioned in any given cell. At each time step, the fluid is advected, and these quantities, like fluid fractions and the geometrical parameters, are updated. The third technique is the GMO, or the general moving object capability. You can see the animation playing on the right-hand side of your screen. The general moving object model is a capability in Flow3D that allows coupled fluid-solid interaction, and which can simulate up to 500 different moving objects, each with its own complex shape and motion type. The motion of each object is independent and can be coupled to the fluid or prescribed, or both. I'll now go over some of the examples. The first example here on your screen pertains to drug delivery. Shown here is the simulation of a medical injection needle. The needle is a few hundred micrometers in diameter, while the syringe itself is a few millimeters in diameter. This is a dramatic variation in scale, and this problem was modeled using an axisymmetric 10-degree mesh in the cylindrical coordinate system. Let me play this animation again for you. This shows a cross-section within the syringe. In this application, it's important to understand the injection force required on the plunger while squeezing out the shear thinning fluid. Strains and shear stresses are calculated to determine whether proteins or cells within the fluid are damaged. This model uses our non-Newtonian viscosity model because the fluid is shear thinning. Flow 3D can include other viscous effects as well, such as thixotropic fluids, temperature-dependent viscosities, a Karoo model or a power law model. To simulate the plunger of this syringe, the general moving object model was used. A prescribed velocity was applied to the plunger. The next example here shows a modeling done for a nasal cavity. Flow 3D is used here to model a nasal cavity to determine flow patterns during drug delivery. Particles with varying densities and sizes are released from a nozzle, and their locations are tracked as a function of space and time. You can see the different colors in the animation on the left-hand side. The colors denote particles with different densities. To model this, Flow 3D used its particle fluid coupling model. A time-dependent mass momentum source is used to release the spray with particles. One feature that makes modeling design variations really easy is Flow 3D's meshing technique. For instance, in this case, any variation in the nasal cavity can be imported into the same mesh and the simulation can be rerun. This next example shows the modeling of evaporation and drying of a droplet of liquid. A common problem that's well established in the literature is the coffee ring effect. And this is essentially the formation of darker regions at the periphery as a liquid droplet evaporates. As a solvent evaporates, it leaves behind the solute. Heat transfer from the surroundings causes the droplet to evaporate more significantly at the droplet edge. This effect, along with surface tension, causes a curvature at the edge. This in turn induces a net flow towards the edge as fluid flows there to replenish the evaporating fluid. This motion moves the solute towards the edge, building up a ring of solute there. Let me just show you what the coffee ring effect looks like. On the left-hand side, of your screen, you should see an image from a coffee ring, and on the right-hand side at the bottom, you can see the simulation of an image from the simulation of the flow generated at the contact line because of evaporation. The marker particles, you can see they pile up at the contact line where the evaporation is greatest. This next example shows how medicine or the dissolution of medicine can be modeled using a Flow 3D. Shown here is the modeling of salt dissolution. Salt blocks are represented by the green components nested in the image on the left-hand side. As flow comes in from the left boundary into the domain, it dissolves the salt. The quantity of solid released, the function of the mass transfer coefficient shown in equation 1 on the bottom left-hand side of your screen. This quantity is also a function of the concentration already in the fluid, so that the higher the existing concentration in solvent, the less of the solute is dissolved from the block. The image at the top right-hand side shows the concentration released into the fluid, and the image at the bottom right shows the shape of the dissolving surface and the mass flux of the salt. The simulation required the new dissolution model. This will be released in February of next year along with the newer version of the code. Because Flow3D has meshing and geometry independence because of the favor method, the area and volume fractions that make up the geometry are simply rewritten at every time step as the solid dissolves from the surface, at the surface. This makes the simulation very computationally efficient because no remeshing is required. I'll now pass the presentation over to my colleague, Joel Jacob. He will talk about some of the other applications in this industry. Joel? Thank you, Shan. Further down this presentation, we can show you moving object model capabilities and mixing applications. We're also going to show you some chemical reaction models, some fluid structure interaction, and talk about surface tension effects. This is an active mixer. Active mixers make use of a mechanical device to facilitate mixing. In the above example, a magnetic stir bar, which is driven by an external rotating magnetic field, is used to induce mixing. The simulation uses a general moving object model, and it simulates the magnetic stir bar. The magnetic interaction of the bar is not included, but instead the rotation speed of the bar is specified directly as a prescribed motion. And the two streams of the fluid come in from the left boundary and mix because of the stir bar, and then they leave from the right boundary. I'm going to play this animation again. Now regarding the physics here, the simulation is set up as a one fluid case where one stream carries a scalar array. In this case, there's no density variation. However, Flow3D can simulate multiple density components as miscible or immiscible fluids. The separation of the immiscible fluids in Flow3D can be based on drift relationships. The prescribed motion can be time dependent. We can have angular velocity based on time. We'll now take a look at passive mixing that's used in pharmaceutical industry or biotech industry for microscale mixing. The ability to mix multiple streams of fluids in microchannels or microchambers within short mixing length and time is important for applications such as bioanalytical system. Passive micromixers make use of geometry of microchannel to induce mixing. As shown here is a design variation where liquid plus the reagent side uses a passive scalar to show mixing concentration. It is important to point out that Flow3D has different viscosities and density mixing as well. We can have up to about 100 scalars. We can have chemical reactions between these scalars, track their concentrations, as well as have them as multiple fluids. We're going to take this one step further and show you how chemical reaction can be applied to mixing. This is a classic example of acid-base neutralization, where we used HCl and sodium hydroxide to form salt. Flow3D has a chemical reaction model where multiple components can create a new concentration. For instance, in this example, we have 20 liters of hydrochloric acid that's mixed with 2 milliliters of sodium hydroxide to make salt. On the very left, you can see the acid, and the base is introduced through a Moss source at the very bottom. We're looking at contours showing concentration of acid and base, and on the very right, you can see salt being formed as a result. Here, an active stir was compared against passive mixing for diffusion only. Now, passively, through chemical reaction, it takes about 437 seconds to reach a pH of 7. However, using a stirrer accelerates the process where it only takes 20 seconds at 4 pi radians per second. Now, this is interesting because usually in pharmaceutical industry, they do want to get this faster. At the same time, they use different impellers, so you can have different impeller geometries and see what angular velocities you need to get a certain pH. The general moving object model was used to simulate the rotating mixer. The chemical reaction model was used to simulate the reaction. And a time-dependent source is introduced as for the base. This is a continuation slide where you can see a pure passive mixing on the very left and a three-dimensional view of the active mixing using a stirrer at 4 pi radians per second. I'd like to show you some fluid structure interaction now. Flow3D has a deforming wall model that can be used to simulate fluid-solid interaction. This could be used, for example, to simulate blood flow in arteries as shown on the left. This animation shows a prescribed motion actuator, the dark gray solid. And nozzle that's transparent, that's made of the deforming material. The fluctuation of the solid creates pressure waves that propagate through the nozzle. As far as the physical details here, the computational cell has a spring constant normal to the surface. This value can be assigned per solid object imported into Flow3D. Also applied in this model is a general moving object model to simulate a prescribed motion of the actuator. Please note that blood is a non-Newtonian fluid, so these moving object models can be coupled with non-Newtonian physics and shear thinning. Flow3D can be used to model piezo-driven micropumps as well. In the next slide, we're going to take a look at how these micropumps can be modeled. Some of these animations are large. Please bear with us. They might take a moment to load. The image on the left shows a piezo device with a flow in, line and out, and the wiring to the supply of power. In this animation, a void pressure is set on the back side of the piezo device, which is a thin horizontal component. Two valves are included in the general moving object model to control the flow direction as the pump oscillates. An oscillating force is applied to move the membrane. This force can be a point or a distributed load. We can also have particles, and here particles are used to visualize the flow. The two images on the bottom right are exaggerated, of course, but they show two different supporting options. One is a clamped configuration in which a moment exists at the edge of the piezo. The other is simply supported, meaning it is treated as if it is pinned. In each case, it is point force applied, which is why the membrane shape appears as it does here. Let's take a look at some surface tension effects. Here we are simulating fluid dispensing at a small scale where surface tension effects are critical. The concern here is the exact volume of fluid dispensed and how much is drawn back into the dispenser. This simulation requires surface tension, which can be constant or temperature dependent in Flow3D. The general moving object model was used to simulate the dispenser motion. So you can have substrates here and nozzles with specific contact angles, where you give an initial contact angle for surface tension, and we calculate dynamic contact angles through the flow. We can simulate both wetting and non-wetting fluids. Another example of surface tension effects. A small mass of liquid moved in or out of part of light beam can redirect it by refraction or reflection into a different path. This concept is particularly attractive in connection with optical fibers, where once a beam enters a fiber, it is trapped by internal reflections. To make optical circuits of any complexity, it is necessary to have a switch that can redirect light from one fiber to another. One concept that has been proposed is based on thermocapillary devices. A small drop of liquid, in this case, is placed in a microchannel that intersects with the fiber optic light beam. And when the drop is moved along the channel to where the beam must pass through it, the beam is reflected into another fiber. This drop is moved by differentially heating its two sides. This causes change in the surface tension in the meniscus on either side of the drop, such that the drop is pulled toward the cooler end of the channel. Eventually, when the constant pressure gradient along the bars, the drop should stabilize in the new position because the surface tension coefficient on each side times the force due to the contact angle should balance out. This also captures the mass transfer in a liquid layer due to surface tension differences, or the Marangoni effect. Since the liquid with a high surface tension pulls more strongly on the surrounding liquids than the one with low surface tension, the pressure of a gradient in surface tension will naturally cause the liquid to flow away from the regions of low surface tension. Flow3D is used in this case to study the time required by the drop to move in response to a particular temperature gradient, and also to predict the drop shape. And finally, on this slide, I would like to point out that in our next release, we'll have a couple finite element, finite difference model, where finite difference techniques solve the flow as well as the thermal flow in the fluid, and the couple finite element model will automatically mesh the solids and simulate solid mechanics in terms of stresses due to external forces and thermal gradients within solids. Meshing is completely automatic, making the model setup very simple. Now, this is not relevant to biotechnology, but it is an example of a cooling alternating housing, which is pulled off from a casting mold, having cooled for about a minute. The image on the left is a plot of mean isotropic stress in dynes per centimeter square. This is a measure of stress magnitude akin to pressure. Negative values indicate regions under isotropic compression, and positive values under isotropic tension. The image on the right is a von Mises stress in dynes per centimeter square at the same point. This is a measure of tearing stresses. Values of von Mises stresses are always positive, and larger values indicate regions where shearing forces are largest. We see several applications for this development with fluid structure interaction, and with this we bring this presentation to a conclusion. We will upload this presentation, and we're planning to have more web presentations regarding biotechnology and pharmaceutical industry. Please visit our website to find details to this presentation should you need to review it later. And always feel free to contact our office at 505-982-0088. Please send us detailed emails if you have any technical questions and if you need to simulate a problem. Thank you again for attending this web presentation. Should you need to email us, please email us at sales@flow3d.com. Thank you again, everyone. Have a good day.